All right, so we finished this example. One thing I didn't mention is notice this thing's not symmetric. It's not a surface of revolution. Okay, so it's less canned, less contrived. We can do more things with the double integral with regards to finding surface area. So that's good. Okay, one more example and then we're done with the section already. Evaluate the surface area of the portion of the paraboloid z equals 9 minus x squared minus y squared above the xy plane. Alright, so we have this formula, but we still have to define that domain in terms of like just how we did this when we were trying to find a volume, for example, of the paraboloid. So different problem, but lots of the same things that need to be done. And finding that domain is not exactly trivial. So notice above the xy plane, a couple approaches you could take here. You could try graphing the paraboloid. It is a function of z in terms of x and y. If you let z equal 0, for example, you could notice that you have a circle with radius 3. So that could help you sketch that. When x and y are 0, you get 9. So it's oriented in this way. I'll let you know when we take a quiz or test on this, which will be a while from now. Exam 4 be our last regular exam in that set, whether I would give this to you or not. But anyway, we need to characterize that domain, and so that is when z equals 0 here, because that's the maximum extent in the xy plane, or that projected up. So we'll see an example like this actually in the next section, where if the paraboloid is oriented the opposite direction, and let's say that you had that radius of 3 on the top at 9, then that would be your xy domain and you have to project it down. So I've been holding your hand a little bit, telling you, hey, by the way, this is easier in polar, but you're going to have to start figuring that out when it's good to use or not, as it comes more comfortable. We'll talk about the test. You know, that's kind of not this. I'll probably just tell you, but I haven't written it yet, so I'll get back to you on that. But now in this section, this is easier to do in polar because this is the polar rectangle, a circle centered at the origin, right? So definitely want to do polar. So we have a lot going on. Now we can start setting up this integral. So two of the ingredients are f sub x and f sub y. Z is solved for here, so that's pretty straightforward, just doing those partials. And then plug them in. We'll definitely want to simplify that, and then we're also thinking about our domain, noticing that our domain and also our function here would be better in polar. So now putting that all together and trying to characterize this integral in polar land, dA is equal to r dr d theta, or r d theta dr, depending on whatever order you want to do it. And then also notice when you simplify on the inside of the root that we get a 4 that can be factored out, and we're left with x squared plus y squared. So converting that equation to polar, that would be equal to r squared. Don't forget the r, that's a really common mistake. And now we have to start putting our bounds in terms of r and theta. So it's pretty easy. We have our r going from 0 to 3, and then our theta goes all the way around. It's not a sector, it's the whole entire circle, so that's 0 to 2 pi. So putting that all together, we have the following. Alright, so take a look at this integral. You could integrate with respect to theta first. It doesn't depend on r. We do have numbers here in the limits of integration, so you can actually split it up into 2, being times each other. It's up to you. Kind of got some options with this one. I decided to split it up and do my integral in terms of theta of just 1, because there's nothing with r in it, or I mean with theta in it, excuse me, so then it'd just be the integral of 1, and then all the r stuff, that integral with respect to r. So the integral with respect to theta is just theta, and then we're going to plug in. Here we want to do a u sub, where u is 4r squared plus 1. You take the derivative of that, and you get 8r. So then we can reformulate that r dr can be substituted as du over 8. That's one way to do that. So my integrals in terms of u now, I can do it. A lot of simplifying going on. And then I plug back in terms of r, plug and chug, and we get an exact result. So don't do silly things like in this root 4r squared plus 1. Because it's plus there, you cannot break that root up. That's a common Calc 1 error that students made all the time. It's like, oh, that'd be really nice if you could do it. Yeah, it would be really nice, but it's illegal in algebra and it's not right at all. So, you do that r, also, if you forget that r, you don't know how to do this integral. Okay? So, not just remembering r is important for the sake of remembering r, like, oh, well, it could be like in this one here that you can't show how to do the integral because you can't do it without the r. So I mean it's pretty important from that perspective that you can't show the integration correctly without it. So that's it for the section. Any questions? Okay, we got another section in our belt.